Hi everyone. Once again, thank you so much for joining this session. In this session, we are now into module 2 of this course. This is week 3 of a 14-week course that we set up to talk about Wi-Fi technology fundamentals. So in module 3, we are going to dive into the physical layer, right? WLAN physical layer. And in today's session, we're going to talk about frequency allocation for Wi-Fi and some basics about modulation techniques and so on. Just before we go into today's session, just a quick recap of module 1 in general. Module 1 was about introduction and history to Wi-Fi. We did 4 sessions, 4 one-hour sessions in this module. The first session talked about evolution of Wi-Fi, the generations of Wi-Fi, how Wi-Fi evolved in the enterprise, in residential environment, and what were the various business applications for Wi-Fi, and we talked about all of those things. In the second session, we talked about network topologies, various ways in which Wi-Fi is deployed, infrastructure mode, bridge mode, ad hoc modes, and so on. And we also talked about various backhaul mechanisms of how Wi-Fi routers connect to the internet. We talked about how they connect using fiber, using coax cables, using cellular networks, using satellite networks, and so on. And also we talked about various use cases on how Wi-Fi networks are deployed. Third session, we talked about standards and how the standardization process works, how IEEE works, how the standards bodies work, and the number of other organizations around the standards bodies that are helping in the development and adoption, widespread adoption of Wi-Fi, like Wi-Fi Alliance and WBA and a number of other organizations, a lot of marketing organizations, engineering organizations, and so on. And we also talked about the various amendments to the standards and how the amendments actually get absorbed into the main standard and how the process actually works. And the last session in module 1, we talked about the basics of a Wi-Fi router. What is inside this access point or Wi-Fi router? What's the difference between access points and routers, and the basic building blocks or functional blocks of a Wi-Fi router. So if you missed any of these sessions in the module 1, they're all available on the course webpage. You can actually access the webpage from the link here, and all the videos of all the 4 sessions are uploaded, class notes, slides, everything is uploaded on the webpage. And you can also register if you're not already registered here. And
sorry to interrupt, but can you remove the picture-in-picture layout on the screen? Yes.
Right. Okay. So now it's all good.
Yes. Now it's
okay. Okay. Great. So yeah. So if as Sainath mentioned, we have over 1,000 participants in the WhatsApp group where we share information about this course, post updates, and so on. If you want to join the group, you can. Okay. So going on to today's topic, we are into module 2, which is the wireless LAN physical layer. So what are we going to talk about in the wireless LAN physical layer module? It's all about the communication between, let's say, a Wi-Fi router and a station device. So this is a Wi-Fi station, this is a Wi-Fi router, and how they communicate with each other over the medium, right? So there are so many ways devices can communicate with each other. We can use cables as a medium. So let's say you have an Ethernet cable here. You can actually communicate over the Ethernet cable. You can communicate over the fiber optics cable. You can communicate over coax cable. And of course, you can also communicate over the air. Right? Wi-Fi uses over the air mechanism to communicate. So what does physical layer, what are the things that we're going to talk about here? The only thing we are going to talk about here is all the routing is taken care of. The packets have reached this access point, and all the internet networking, everything is taken care of already. All we have to do is we now have to carry bits and bytes of information from this antenna to this antenna. How do we carry that information from here to here? Is all that what we're going to talk about in this particular module. So information flowing from here to here over the air. It sounds simple, but it is actually quite complicated. If it is a scenario like this, where there is what we call as a line of sight, where the transmitter can directly see the receiver and they're very close to each other, then the communication is fairly straightforward. But that's not how the real world works. The access point could be behind a wall, it could be behind some other building, there could be all kinds of interferers, and also there could be other devices trying to talk to the access point. We need to figure out at what speed we want to communicate between them, And all these things we need to figure out. We need to figure out how to operate in the presence of interference, in the presence of obstructions, when the receiver is very far from the transmitter. All these challenges that are happening in the real world because of a wireless link. And these problems don't exist on the wired network for the most part between these two points, because you can run a wire, and normally when you send signals on a wire, it's not really prone to interference that much, right? And so it is a fairly easy process. But in the wireless world, all these other things come into the picture: interference, obstructions, and distance. All these other things come into picture and play a very big role. And what we are going to talk about, all those different challenges and how successfully a transmitter can send information to receiver in different kinds of conditions and environments. That's what we're going to talk about in this module. So we're going to start today with frequency allocation and modulation basics, how unlicensed spectrum works, the various channels, channel bandwidths. We're also going to touch on spectrum technology and so on. As we go on in this module, we're going to talk about modulation, coding. We're going to talk about multipath. What is the concept of multipath? What is the concept of delay spread? And we're going to talk about multiple input, multiple output, MIMO technology, OFDM. What is the concept of spectral efficiency? We hear about spectral efficiency a lot in wireless communications, in Wi-Fi. What does that mean, and what is the concept behind it? Those of you who are in the Wi-Fi space, you hear this term MCS table a lot. So what is this MCS table? How do you actually calculate all these rates? How is the table created? And what are all the different parameters there? How are you getting different levels of throughput? When you're actually looking at the box of a Wi-Fi router, it will say it can do 54 Mbps or 100 Mbps or 2 gigabits per second or 10 gigabits per second, different throughputs. How are you achieving those throughputs? What are you doing at the physical layer to achieve those throughputs? And the last session here, we're going to talk about physical layer headers, how the protocol between the two devices works, how do you use the headers to communicate different information between the transmitter and receiver, and what are the key functions of the physical layer and sublayers. We're going to talk about those things in this module. So let us get started with the first session, which is frequency allocation and modulation basics. Right, so before we look into the frequency allocation, we need to talk about frequency spectrum. So as humans have a certain range of frequencies in which we can actually hear. So these are called, of course, sound waves. And these waves normally operate between 20 hertz and 20,000 hertz. That's the range in which humans can hear to what's happening. Of course, there are so many other different types of signals and waves that go on around us, which we cannot hear as humans. But that does not mean they don't exist. They exist. In fact, the other animals can hear them. And of course, transmitters and receivers can talk to each other using those frequencies. But there is only a very small frequency range in which us humans can actually hear what's going on. Now, if you look at other animals, there are dolphins, bats, and others. Dolphins can have a much wider range of frequencies. Bats, rats, dogs, and so on. They have a different range of frequencies in which they can basically communicate and listen to information. If you look at the wider frequency spectrum that is available, it starts from very low frequency all the way from like 10 hertz and goes all the way up to like megahertz, gigahertz, terahertz, petahertz, and exahertz, right? So it's like really, really, really high frequencies. As you go up the frequency spectrum, you are moving from radio waves, microwaves, to infrared waves, to light, visible light, to ultraviolet light, to X-rays and gamma rays, right? So that's these are the as you go in this spectrum, the higher the frequency, those are the different types of rays that you would see in the frequency spectrum. Now, what we are talking about, where Wi-Fi is operating, is within this range of radio frequencies, and within the radio frequency range, this is where Wi-Fi is. It's in the 2.45 gigahertz, and now in the 6 gigahertz, like between 2 gigahertz and 7 gigahertz. Within that range, you have a list of unlicensed frequencies that are available that are actually used for Wi-Fi transmissions. And some of these licenses are opened up for unlicensed use. As I mentioned in one of the sessions before, the government lets people to use those frequencies as long as they meet certain requirements. They allow them to use without paying anything. It's free for people to use those frequencies. So Wi-Fi operates in that spectrum between around the 2 gigahertz range to the 7 gigahertz range approximately. Okay, so as I've mentioned here, there are like 3 bands in which Wi-Fi operates. The first band that was opened up in the very early stages of Wi-Fi was called the ISM band. Within the ISM band, there was a spectrum of about 80 megahertz that was opened up between 2.4 gigahertz and 2.48 gigahertz. There was about close to 75-80 megahertz of spectrum that was opened up, and that was kind of broken down into approximately 3 non-overlapping channels, and each channel is about 22 megahertz wide. So that's where you get channels 1 through 11 in the US, and it goes up to 14 in other countries, but these are all overlapping channels. And then there are 3 channels here that are non-overlapping, channel 1, 6, and 11. This is the 2.4 gigahertz ISM band. Now, what is the band? What is spectrum? What is channel bandwidth? What is frequency? I'll get into all these details in the next few slides. In the 5 gigahertz band, later when 11A technology came out, they opened up spectrum in the UNII bands, UNII bands. This is in the 5 gigahertz range. So there are some frequencies that were opened up for unlicensed use for Wi-Fi, and these frequency ranges are from about 5.1 gigahertz to about 5.8 gigahertz range. So it's about close to like 600 something megahertz of spectrum that was opened up for unlicensed use. And again, that spectrum is broken down into channels, and you can have individual access points and devices communicate over multiple channels. Just like the 2.4 gigahertz band was broken down into 11 channels or 14 channels, of which 3 are non-overlapping. Similarly, in the 5 gigahertz spectrum, you have number of non-overlapping channels, and these are the channels. So you can see channel 36, channel 40, channel 44. If you're using 20 megahertz wide channels, then you have all these non-overlapping channels. If you're using 40 megahertz channels, then you combine the 2 channels like 36 and 40, and that will become 1 channel. And so these are the non-overlapping 40 megahertz channels. So you can see that around the 600 plus megahertz of spectrum that is available is now broken down into channels, and multiple access points can operate individually on all these channels. And based on what channel bandwidth you use, 20 megahertz, 40 megahertz, 80 megahertz, 160 megahertz, you can actually have a different number of non-overlapping channels in the 5 gigahertz band. Now, recently we have 6 gigahertz band that is opened up, and as we can see here, 6 gigahertz band operates between the 5.9 gigahertz to the 7.12 gigahertz range. So this opens up about 1.2 gigahertz of spectrum. So that's 1200 megahertz of spectrum, and this is much wider spectrum than the 5 gigahertz band. So this is now available in certain countries, not all countries, but in some countries, this additional spectrum is available. This is part of the Wi-Fi 6E technology, where you're using the 6 gigahertz. Now, if you look at these 3 spectrums, 2.4, 5, and 6 gigahertz, you can see that if you look at the various parameters, if you look at the available spectrum, 2.4 gigahertz has the lowest amount of spectrum available, 5 gigahertz has higher, and then 6 gigahertz has the highest. When it comes to range, 2.4, since it's the lower frequencies, it provides you the highest range. The lower the frequency, the more the wavelength, and the longer the range you can get for your transmission. So 2.4 gigahertz gives you the highest range, 5 gigahertz is lower, and 6 gigahertz is the lowest. As far as how crowded the spectrum is, since 2.4 was released early on, it came out first. There are a number of other technologies that are also using the same 2.4 gigahertz spectrum, Bluetooth, cordless phones, baby monitors, and so on. And so that spectrum is fairly crowded. And all the legacy devices access points, a lot of them operate in 2.4 gigahertz. So there is that particular spectrum is actually very busy and crowded. If you look at 5 gigahertz, it's a little bit lower when it comes to how crowded it is, and 6 gigahertz is the lowest, and it's the most available spectrum because it's the most newest technology that is available when it comes to Wi-Fi usage. Data rates, 2.4 gives you the lowest, 5 gigahertz you higher, and 6 gigahertz gives you the highest data rates. These are some of the advantages and disadvantages and things that go on with these different kinds of spectrum that is available. Now, if you look at the 6 gigahertz channel allocation in more detail, as I said, there's about 1200 megahertz of bandwidth available, and that is again broken down into lots of small channels. If you break them down into 20 megahertz channels, then you get about 59 channels, 59 non-overlapping channels that are available for use. And if you break them onto 40 megahertz channels, then are about 29 channels. And then if you're doing 160 megahertz, then there are about 7 channels available. And Wi-Fi 7 also allows you to do 320 megahertz channels. Then you have about approximately 3 channels, 320 megahertz channels that are available, that are non-overlapping. And for each of these channels, there are again restrictions. Right? So if you look at what is shown in this picture, the boxes that are just solid blue in color are low power indoor only. So which means that you can only use them for indoor use and at a lower power. But then the ones that have a green border at the bottom, these channels can be used for low power indoor plus also outdoor usage. When you turn on this feature called automatic frequency coordination, or AFC, AFC has a certain set of rules that you have to follow. As long as you follow those rules, then you can operate in the outdoor environment also. And what is AFC? What are those rules? We will actually cover that when we go through the Wi-Fi 6E module session that will come several weeks down the road. So this is the 6 gigahertz channel allocation. As you can see, when compared to 2.4 and 5 gigahertz, there is a lot more spectrum and a lot more channels that are available for use. And again, as I mentioned before, this is not yet available in all countries. In certain countries, this spectrum is now available for unlicensed use. So these are some of the power restrictions for both 5 gigahertz and 6 gigahertz. I'll not go into the detail in the interest of time, but the slide is there for you to look at what are the transmit power restrictions for various channels in the UNII bands across all the way from UNII 1 to UNII 3, that's in the 5 gigahertz spectrum, and then UNII 5, 6, 7, 8 in the 6 gigahertz spectrum. What are the power restrictions? What is the maximum power you can transmit? All those details can be found here, or you can just Google for it and find those details. Okay, so now coming to some basics. We are throwing a lot of words at you. We're talking about spectrum, frequency, channels, channel bandwidth. If you are coming from the Wi-Fi world, you will most likely understand all of these things, or most of these things. But if you are new to this Wi-Fi world, a lot of these things could be quite confusing. So let's go to the basics and start from the basics. So what is a waveform, and what does it do? What does frequency mean? What does this kilohertz, megahertz, gigahertz? We're talking about all these things. What do they actually mean? So if you want to explain in very, very simple terms, information or energy, when you're sending information from here to here, from the transmitter to the receiver, that information moves in the form of waves. Right? Why it moves in the form of waves, we'll talk about it in the coming slides. So when it moves in the form of waves, the frequency at which that waveform moves is referred to as the frequency, or in other words, called cycles per second. So what is a cycle? A cycle is one complete movement of a waveform from 0 degrees all the way up to 360 degrees in phase. So this is one cycle of a waveform, of a sine wave. So what is frequency? Frequency is the number of cycles per second. Cycles meaning repetitions of this particular waveform within 1 second. If this particular cycle repeats 4 times within a second, you can see that it's repeating 4 times within the second, then that is 4 cycles per second. And that is nothing but 4 hertz. So the frequency is measured in the units of hertz. So what we are saying here is this particular sine wave or wave basically completed 4 cycles within 1 second, and so it is the frequency is 4 hertz. This is not the speed at which the wave is traveling. That's different. Electromagnetic waves and all these other waveforms travel at the same speed, at the speed of light. I'm not talking about how fast these waves are traveling over the medium. So that's different. This is just how the cycles of the wave and how frequent these cycles are within a certain period of time, and that's what represents the frequency of the signal. So just to remind again, like if you're doing 4 cycles in a second, that is 4 cycles per second, that's 4 hertz. Now go to like megahertz, gigahertz, kilohertz, and so on. So hertz is nothing but cycles per second, as I said. Kilohertz is a kilo of hertz, which means 1,000 hertz, right? And that's the unit. And megahertz is 1,000 kilohertz, and gigahertz is 1,000 megahertz. So if you are saying 1 gigahertz, that is 1 billion cycles per second. That means that this particular cycle has repeated 1 billion times within a second. And that's how you get 1 gigahertz. So now if you're saying 2.4 gigahertz, then that means that particular waveform has cycled 2.4 billion times in a second. And that's how you get that frequency, which is pretty awesome, right? So that's how hertz and gigahertz and megahertz are measured. Now, radio waves, as I was mentioning about the frequency spectrum, they operate within around the 3 kilohertz range, all the way up to 300 gigahertz. So they can go pretty high up. And of course, all the other waves we talked about, X-rays, gamma rays, and all of that, they can go much higher. But most of the radio waves, radio frequencies we're talking about are within this range. This is the range in which we have TV communication, satellite communications, FM radio, AM radio communication, radar communication, and of course we also have wireless LANs, and also we have cellular networks. We have all these other technologies that use the frequencies within this range. So that's just a quick overview about what all these kilohertz and megahertz mean. So let's get back to even more basic stuff. Okay, what is a wave? We are all talking about these waveforms. What is a wave? A wave is just a traveling disturbance that transports energy from one location to another location. So if you're transporting energy, meaning you're sending information in the form of energy. So when you're sending information, ones and zeros, from the transmitter to the receiver, that information is sent in the form of energy. And energy travels in the form of waves, right? So that's basically what a wave is. So some terminology here. The energy being transmitted from the transmitter to receiver is called a wave, and then the medium through which the wave is being propagated from here to here is called obviously the medium. So in this case, the medium is wireless medium because there are no wires attached. So the energy from here to here is being transmitted in the form of a wave over the medium, which is air. Now, if I drop this access point and phone inside water, now and I'm sending signals from here to here, now the medium is water. So the same signals are being propagated through the medium called water. Right? Similarly, the medium can change, but the energy can be transmitted in the form of waves. Now, the process of sending the energy from here to here is called propagation. So the signal moving from here to here is called propagation. So if you look at an example of a wave, that's normally how any wave looks like, and like the highest part of the wave is called the crest, and the lowest part of the wave is called the trough. And all transmissions, it could be wired or wireless, the energy is being transmitted in the form of waveforms from one place to the other, from the transmitter to the receiver. But why waveforms? This is a question that I always have, and I still don't have a very clear answer. I'll try my best to explain this as per my understanding, but it's always very curious to me of why should energy from here to here travel in the form of a wave? Why can't it just go straight from here to here? Why does it have to go in a waveform? So that's a very interesting question. And to actually answer that question, if you look at a simple example of any kind of a periodic motion, like a pendulum. If you have a pendulum, as I was seeing in this example, the pendulum swings from left to right like this. And as this pendulum swings, as the energy goes, as the bottom part of the pendulum goes all the way to the highest point, it actually slows down. And then that is when it has what we call as the highest amount of potential energy. So there's a lot of all the energy in that unit is saved in the form of what we call as a potential energy. So potential energy normally doesn't is not the energy that you have when the system is not in motion, right? And when it actually starts coming down, that potential energy gets converted into kinetic energy. And as you get to the bottom part here, that is when the unit at the bottom is at its fastest speed, and that's when it has the most kinetic energy. And then as it goes all the way up to the right hand side, again the kinetic energy will go down, the system will slow down, and it will gain potential energy. So the energy is being constantly converted between potential energy, kinetic energy and back to potential energy as you move the pendulum, right? So now if you're doing the same thing with the spring, for example, if you're trying to pull down on a spring and leave it, as the spring goes all the way up, it will stop or slow down. It will gather all the energy in the form of potential energy, and then that pushes the thing back, and as it comes down, it gains speed, and then that energy gets converted into kinetic energy and back to potential energy and so on. Now, while this is happening, the signal, it's not like it's going to continuously keep doing that at the same speed. As you can see in the case of pendulum, over a period of time, the pendulum will slow down because of resistance, right? As there's resistance in the medium, the pendulum will actually continuously will be slowed down. If you have a pendulum clock, you need to have some external energy source, like some form of current or something that would introduce energy into the pendulum to actually make sure it's swinging at the same pace. If it doesn't have any source of energy, then it will dampen and slow down, right? But as long as it has a source of energy, it is constantly switching between potential energy and kinetic energy. If you look at the same example of when you drop a drop of water into a pool, right? You can clearly see that the energy that it generates is now being transmitted, propagated in the form of waves, right? You can see that you drop a drop of water and then that generates some energy, some disturbance, and then as it starts traveling, it starts getting resistance, and because of that, it slows down, and the kinetic energy gets converted into potential energy, and it actually goes up, and then as it goes up, it basically stops at a point where it has maximum potential energy, and then goes down in the form of kinetic energy, and that process keeps continuing. And that's how energy is normally transmitted between any point to any point in the form of waveforms. That's my best explanation that I can think of. If anyone has any better explanation, or if you think that what I said is not appropriate, please do send message to me. I'd love to hear from you. Okay, so how do you actually generate waves in an electronic circuit, right? Because this one has a bunch of circuits in it. It's okay, I'm not dropping a drop of water on this to generate the waves. This is generating the waveforms somehow. Okay, so how is it doing it? And at a very, very basic level, of course, this technology is extremely complex. There is so many things to it, formulas, equations, all kinds of transistors, resistors, all kinds of components are there. I am not going to go into all those details, but I'll try to explain it in a very, very simple LC circuit concept, where you have this component called an oscillator. Is basically a source of generating these waves, right? In one of the electronic components. So what an oscillator is doing is it's transmitting current between what we call as a capacitor. A capacitor stores electric field, and an inductor stores magnetic field. And as the current is being transmitted, the energy is now being basically moved from the capacitor to the inductor. So the capacitor gathers the energy in the form of electric fields, and then from there it actually goes and charges the inductor, and then the inductor in the reverse order comes back and charges the capacitor. And as this process is going on, the polarity reverse of the current reverses, and because of the constant shift between the electric energy, the energy from the inductor to the capacitor to the inductor, just like we're talking about the pendulum, kinetic energy to potential energy, that generates these waveforms, and these waveforms are then transmitted. Now, of course, how do you control the frequency of the waveform? The control of the frequency of the waveform can be controlled by actually changing certain parameters on the circuitry, which will generate these periodic waveforms at a much higher periodicity or a much lower periodicity. And based on that, you can get different frequencies of signals that are being generated. Okay, so what are the fundamental properties of a periodic waveform? Right? So we talked about frequency. So that's a fundamental property. Frequency, as I mentioned before, is the number of cycles within 1 second. And the higher the frequency, there is something called as a wavelength. What is a wavelength? A wavelength is the distance between any two similar points within a waveform. Like, for example, if you take the crest of the top of the two periodicity of the waves, the difference between, you can see here, this is called the wavelength. The distance between this point in the wave and the exact similar periodic point in the wave, and that's called the wavelength. Now you can see that higher the frequency, more periodic the wave is, lower the wavelength. So wavelength is inversely proportional to the frequency. So basically higher frequency waves have shorter wavelengths and lower frequency waves have longer wavelengths. So that is one of the properties of a periodic waveform. What is another property or another characteristic? It's amplitude. Amplitude is basically the power level of the waveform. So the higher the amplitude, you're transmitting at a higher energy level, right? And it's like, for example, when I'm speaking very at a low voice, my amplitude is lower. When I'm speaking at a loud voice, I'm actually generating the same sound waves, but the sound waves will have higher amplitude. So I can generate sound waves at a lower amplitude, or I can generate sound waves at a higher amplitude just based on raising my volume. So that's the amplitude. So any waveform could have lower or higher amplitude, and amplitude is one of the key properties of a periodic waveform. And the other one, which is could be a little bit confusing, is the phase. Phase is an important characteristic. Phase is basically phase is relative. It's not absolute. So while amplitude and frequency are absolute, phase is more a relative property. What does that mean? Phase involves the relationship between the position and amplitude and crests and troughs of two waveforms, right? So for example, if you see waveform 1, which is in blue color, and it's being transmitted like this, and then the second waveform is moved by 90 degrees, shifted by 90 degrees, then there is a phase shift of 90 degrees between this waveform and the second waveform, and so that's called phase shift. So you can shift the phase of one wave with respect to the other, and that's how the phase part works. Normally within a particular waveform, the starting of the waveform here is represented by 0 degrees, and then the crest here, the first crest, is represented by 90 degrees. This point is 180 degrees, and then the trough is 270, and then back to 360, and this is one waveform, and then this repeats again, right? So if you shift by 90 degrees, then you have a phase shift of 90 degrees between the two waveforms here. So just to summarize again, some of the properties are amplitude, frequency, which is directly related to wavelength, and then phase. These are the important things that we need to know. And then we hear this term called channel bandwidth a lot, right? So we said the 20 megahertz channel bandwidth, 40 megahertz channel bandwidth, 160 megahertz channel bandwidth. What does the channel bandwidth actually mean? And it is also interestingly measured in hertz, right? So if you look at the 2.4 gigahertz spectrum, you can see that there are about 14 channels here, and we said that there are 3 non-overlapping channels. And if you take an example of channel 6, so this is 22 megahertz wide, and so the channel bandwidth is 22 megahertz, right? And that is between 2.42 gigahertz and 2.44 gigahertz. This is where you have about 22 megahertz of channel band. So how does that actually work? What does it mean? What does channel bandwidth actually mean? So let's take an example. Let us say this waveform has a frequency of 2.42 gigahertz, and this waveform is actually traveling at 2.42 billion cycles per second, right? And then as you increase the frequencies, you can see the waveforms are being transmitted at higher frequencies, right? And if you go to, let's say, all the way up to 2.44 gigahertz, which is like 2.44 billion cycles per second, let's assume that this is that waveform. So channel bandwidth means that you can use all the frequencies that are between these two frequencies. So between 2.42 and 2.44, you can use all frequencies for your transmission. So if you say that you have 20 megahertz wide channel, that means that the information can be sent on all these frequencies that are between 2.42 gigahertz and 2.44 gigahertz. You can use all frequencies, right? That's what channel bandwidth actually means. Interesting, that's also measured in hertz. So that's the reason why it could be sometimes confusing. But 20 megahertz really means that there is 20 megahertz worth of frequencies, different frequencies, so that you can be used to actually carry information or carry data. So hope that part is clear when it comes to channel bandwidth. Okay, so now the interesting part, like, okay, it's fine, we are saying all these waves and we are talking about amplitude and frequency and phase and all of that. That's all great, but how is this useful for me? How do these waves actually carry information? Because at the end of the day, if they cannot carry information, if they cannot send me bits and bytes from this point to this point, then all of this, what we're talking about here, is completely useless, right? So the whole idea here is we want to send information over these waveforms. And so how do these radio waves carry information? As a simple example, let's take the property of amplitude. Let's assume that we have a wave that is being transmitted at one frequency, it's at a certain frequency. But let's assume that you are sending that wave at a lower amplitude. You can send the wave at a lower amplitude, like just the way I'm speaking. When I'm speaking, my voice is generating sound waves at a certain frequency, but I speak at a lower volume, then it's, as I mentioned before, it is generating sound waves at a lower amplitude, right? So the transmitter can transmit at the same frequency, either at a lower amplitude or at a higher amplitude. That's one thing it can vary, one property it can vary. Now, if you vary the property, how can you carry the information? For example, let's say I want to send a series of ones and zeros, which is basically my information. So I want to send 1 0 0 1 1, that information. So all I have to do is I have to say, okay, to actually transmit a 1, I will start sending the waves at a higher amplitude. And then after a certain time, I want to send a 0. So I will send the same signal, the same frequency, but now at a lower amplitude. So every time I'm sending the information, the signals at a higher amplitude, it is a 1. And every time I'm sending at a lower amplitude, it is a 0. Right? So I'm sending a higher amplitude, then I'm sending lower amplitude to do 0, and again lower amplitude to 0, and again higher amplitude to do 1, and again the higher amplitude to do 1. Now this is an agreement between the transmitter and receiver. The transmitter and receiver have already agreed that whenever I'm sending a 1, you need to know. So the transmitter is telling the receiver, hey, Mr. Receiver, whenever I'm sending a 1, I am actually sending the signal at a higher amplitude. And whenever I'm sending a 0, I'm sending it at a lower amplitude. Now you should listen accordingly. So when the receiver receives the waveforms, it says, oh, okay, I just received something at high amplitude. That must be a 1. And now I received something at a lower amplitude. Oh, that must be a 0. So that is an agreement between the transmitter and receiver. And as long as they have that agreement, and as long as you're varying the property of amplitude, you can actually carry information in the form of ones and zeros. So that's one example. Another way you can carry information is using the other property, which is frequency. Here, you don't have to vary the amplitude. If you see these two signals, they are the exact same amplitude, but you're varying the frequency. So now there is an agreement between these two guys. Now what the transmitter is saying is, okay, whenever I have a 1, I am going to send it at a lower frequency, which means lesser cycles per second. And whenever I have a 0, I'll send it at a higher frequency. Right? So if I want to send the same information like 1 0 0 0 1, initially lower frequency, then higher frequency, then higher frequency, then higher frequency, then another lower frequency. And that's how the receiver will know that the transmitter is actually sending 1 0 0 1. So you are using the properties of the waves that we talked about, amplitude and frequency, to actually now carry information on these waveforms. That's the basic idea. So now we'll come to what is actually modulation. So modulation is nothing but, there are so many definitions and so many things about modulation, but at a fundamental level, modulation is the process of varying one or more properties of a waveform, a periodic waveform, and that is used to carry information. So we varied the amplitude, which is one of the properties, we carried information. We varied frequency, that is one property, we carried information. So if we are varying the frequency, it is called frequency shift keying or frequency modulation. If you are varying the amplitude, it's called amplitude shift keying or the amplitude modulation. If you are varying the phase, remember we talked about phase also, right? So the same concept can be applied for phase. If you want to send a 0, you send it at 0 degrees phase shift. But if you want to send at 1, maybe you shift the phase by 180 degrees. And then you start sending it that. As long as there is a phase lock between the transmitter and receiver, the receiver knows that if I am receiving the signal at 0 degrees phase shift, that must be a 0. And if I am receiving the signal at 180 degrees phase shift, then that must be a 1. So that is an agreement again between the transmitter and receiver. So if you're using phase, you're varying the property called phase to carry information. That is called phase shift keying or phase modulation. Now those are the simple modulation techniques. Now there are more complex ones like quadrature amplitude modulation or QAM. Most of you who are here in the Wi-Fi world, might have heard about QAM, and we talked about 16 QAM, 64 QAM, 256 QAM, Wi-Fi 7. Now we are saying it is 4K QAM or 4096 QAM and so on. So what is this QAM? QAM is where you are varying both the amplitude and phase to carry the signal. In the first three methods, here you see when the frequency is being varied, the amplitude and the phase are fixed. So when the frequency is varying, you can see that the amplitude is not changing. The amplitude is fixed, and the phase is also fixed. When you're doing amplitude modulation, you see that the frequency is not changing and the phase is not changing. So in these three modulation types, you're only varying one property at a time. And because of that, you'll not be able to carry a lot of information. Now, if you want to carry a lot more information than you normally do with FSK and PSK, then you can use this QAM technique where you are varying both the amplitude and the phase at the same time. Now you are able to carry more information. For example, you can say a phase of 0 and an amplitude of 1 represents not 1 bit, but it represents 2 bits, 0, 0, 0, right? So by varying both the amplitude and the phase, you'll get more combinations. And because of that, with one signal or one symbol, you'll be able to transmit more bits rather than 1 bit. And this allows you to carry more information, and that allows you to get more throughput, right? So it might be still confusing, but I can try to explain it within the time we have. And I'm also going to put some references here. Again, if it's not clear to someone, you can certainly reach out to us, and we're happy to explain it in more detail. Some of the parameters we talked about here, in the interest of time, I'll not go through them here, but you can certainly go through the notes, and each modulation has advantages and disadvantages, and those are listed here. Okay, so now we said, fine, we have information and we have digitized it in the form of ones and zeros. We said, okay, we have waveforms, signals on which we can transmit ones and zeros. So those signals are called information signals. That's great. So we have the information signals. But now, how are we going to send the information signals from here to here? You cannot just send the signals, because there could be multiple people trying to talk between the transmitter and the receiver. So if all of them are using the same frequencies or things like that, there will be all kinds of problems. So what will happen is, this information signal is called kind of the baseband signal, right? And that has to be put on what we call as a carrier signal. For example, you are transmitting a 2.4 gigahertz spectrum frequency channel in the 2.4 gigahertz band, right? Channel 1. So what is the 2.4 gigahertz? It's what we call as a carrier signal. So we take the information signal, which we can represent here like a courier boy, for example, and he's collected the information in the form of ones and zeros, in the form of signals, and now that needs to be put on a carrier signal, which is at a much higher frequency, right? That is represented by this car here. So the courier boy gets onto the car, and actually information sits on top of a carrier signal, and now the information is sent from one point to the other point. Now, if you want to make sure that different people are not sending information at the same time and they're not interfering with each other, then each courier person boy would use a different carrier signal. If you're doing frequency division multiplexing, right? So you use different carrier signals to transmit, and that's how you can actually have multiple communications at the same time without any problems. Just like when you tune into the FM radio, there are multiple programs that are going on in the FM radio on different channels. They're all being broadcast at the same time, right? But when you tune into a certain frequency, that information for that channel is carried on that carrier signal, and another information from another channel is carried on a different carrier signal, and they're all unique carrier signals. And when you tune into a carrier signal, then you only listen to the information on that carrier signal and not the information on any other carrier signal. So that's what's called as a carrier signal. So information signals are then put on carrier signals, which is also part of modulation. So if you can see on the charts on the right hand side, you have the message signal, and then you have the carrier signal, which is at a certain frequency, and then when you put the message signal on top of the carrier signal, then you get the frequency modulated signal. This is the actual signal that's being transmitted over the air. Okay, so we will talk a little bit about different multiple access techniques. So far we said, okay, this guy is transmitting information. This guy, he's a transmitter, he's the receiver. But as I mentioned, there could be multiple transmitters and multiple receivers all trying to communicate at the same time. So how are you? That is what's called multiple access. There are multiple transmitters trying to talk to multiple receivers without interfering with each other. So we need different types of multiple access techniques for that. So there is something called as basically frequency division multiplexing. You can imagine of this as there are multiple lanes on the road, and on this axis you can consider them as different channels, and then you have different carriers being transmitted on different channels. So user 1 uses this channel, and user 2 uses this channel, user 3 uses this channel. That is the standard frequency division multiplexing, which is used by AM FM radio example I was talking about. The user uses only that channel and no one else uses the channel, so there is no interference. So that's the standard frequency division multiplexing model. So the disadvantage of this model is that it's not very secure. So if for some reason some hacker wants to get onto this channel and tries to basically tune into this channel, then they can listen to all this information on this channel from this user. To avoid that problem, they started this concept called frequency hopping spectrum, where the user can hop between frequencies. So user 1 can use the x-axis here is time. So in time instant 1, he can use this channel, and then in time instant 2, he can use this channel. In time instant 3, he can use this channel and carry information. So you can hop between frequencies, and then channel user 2 can do the same, user 3 can do the same. That's called frequency hopping spectrum, which is one of the earlier forms of spreading mechanisms that were used in Wi-Fi technology. The other interesting one, what we call as the direct sequence spectrum. This is quite interesting because what they did here is they said, I am going to take information and I'm going to spread it over the entire bandwidth that is available. So if you have 20 megahertz of bandwidth, I'm going to take the information and spread it across that. I don't need all that bandwidth, but I am actually going to spread that information across the entire bandwidth and transmit information. So that improves the reliability of the communication. It actually decreases your throughput and spectral efficiency quite a bit because you're not using all the frequencies efficiently for multiple access, but it increases your reliability because you're spreading the information across a wider bandwidth. The chances of the communication becoming error prone is low, and this is specifically done for indoor environments, because in the indoor environments we have all kinds of issues, multipath and so on, and because of that you are very prone to interference and things like that. And so this kind of spreading the signal across the entire spectrum actually helps you deal with those kinds of noise situations better. And so that's what the direct sequence spectrum technology was used. And then after that came OFDM, or orthogonal frequency division, which is kind of, it goes the opposite way. It actually takes the channels that are available here and it actually breaks them down into multiple sub channels called subcarriers, and smaller sets of information are transmitted over the subcarriers. So this is another form of multiplexing technology where different sets of data can be carried over frequencies. So I wish I had more time to explain this in more detail, but since we are running out of time, I'm trying to kind of explain this at a high level. So what is spectrum, right? As I was mentioning before, you take a base signal and you use some form of a spreading code or a spreading sequence, and you spread that information across a wider channel. So there are two methods that are used: frequency hopping. So you apply basically a random pattern, and if you want to send information, this x-axis is time, the y-axis is frequencies. So within each time slot, you apply when you apply a code or a pattern. So let's say the pattern says the first pattern is 0101. That means that you use this table, the frequency table, and say, okay, 101 means I need to transmit on 700 kilohertz. So now you send that packet on, or that set of information on 700 kilohertz frequency. And then you keep hopping. Every time instant, every hop instance, you keep hopping between frequencies and you send information that way. That's how frequency hopping spread spectrum works. Direct sequence spread spectrum, on the other hand, takes information and then it spreads it across the entire spectrum. So for example, if you want to transmit a binary 1, right? So it's only 1 bit. You want to transmit 1 bit. But what you're doing is you're now applying what we call as a pseudo-noise sequence or a PN sequence. That is a sequence of bits that is applied to this 1. So now this 1 is actually, which is only a single bit, now it's converted into like 10 bits. So that means that information is spread across the entire frequency spectrum, and each one of these bits is sent on and across the entire spectrum. So now you are actually taking one bit of information and you are adding like almost 10x overhead to it, right, to actually send the. And why we do that? Because it increases the reliability a lot. Now the amount of information you can send is very low, and because of which the data rates are very low, but the reliability is much higher. So this is what is called the direct sequence spread spectrum mechanism. So if you look at how direct sequence spread spectrum technology works, you look at a transmitter and a receiver. On the source, you have the base set of ones and zeros you want to transmit, and then you use this code generator that spreads the signal using this code into this wide signal, and then you, of course, you use the RF modulator to modulate the signal onto the carrier signal, and then you transmit it. On the receive side, the receiver receives it. It takes the base signal off of the carrier signal by demodulating it, and so then you have the base signal, receive signal, and then you have the opposite of the code generator, which takes that spreaded signal and then applies the code and creates the despreaded signal, which is the base data set that was originally sent from here, and then it processes that information and sends it to the receiver. So that's how the whole transmission reception actually works when you're using direct sequence spread spectrum. Now, to achieve the different data rates, some of you might have heard in the .11 standard 1 Mbps, 2.5 Mbps, 2 Mbps, 5.5, 11 Mbps. They use different code lengths. So you see this one is called chips or code bits. By using different lengths of codes, you can actually get higher different data rates. So if you're using a smaller length, like for example, an 8 chip code length, that means that you're using lesser number of bits to encode the data. That means that you can get higher throughput, right? So that's how you achieve this 5.5 and 11 Mbps. And you can also change the modulation rates. We talked about BPSK, QPSK. We didn't talk about those things yet. In the next session, we are going to get into all the complex modulation methods like BPSK, QPSK, and all of that. But by varying that also, you get different data rates. So this part we'll go into more detail in the next session. So the last point here is OFDM, and again, I have very little time to explain this, but it's hard to explain this in a small amount of time. But if you look at OFDM is one of the newer multiplexing mechanisms. Remember, we said frequency hopping, that hops between various frequencies. Spread spectrum, direct sequence spread spectrum, which spreads the signal across the entire spectrum available. And OFDM does something different. Now, as we went from the base standard like 11B, where throughput was not an issue, people did not care about throughput. And the reason why frequency hopping spread spectrum and direct sequence spread spectrum were used early on is because they did not expect that people would want like gigabits of throughput. They expected it to be at low data rates, 1 Mbps, 2 Mbps. And in those days, 1 Mbps and 2 Mbps are very high data rates, right? So we could easily achieve those using those techniques. But if we want to really increase the throughput, you have to use the spectrum more efficiently. You cannot just spread the signal across the entire spectrum and wave spectrum. You have to use the spectrum more efficiently, which means that you have to pack more bits on each signal that you send on the spectrum, and you need to send more information in a packed format in the available spectrum. Remember that the amount of spectrum available is the same. That's not changing. So when you say 20 megahertz channel, the 20 megahertz channel was the same for .11, same for .11b, 11a, 11g, 11n, 11ac. It's the same, but the speeds increased. So which means that you're taking the same 20 megahertz channel and somehow you are able to use the spectrum more efficiently. And that is what's called as spectral efficiency. If you can use that spectrum more efficiently, it's called spectral efficiency. What that means is now you're able to send a lot more information in the same amount of frequencies that are available. So as you can see, the techniques like OFDM are a lot more spectrally efficient when compared to the spread spectrum techniques. And that is the reason why we use those methods in 11N, 11AC, and 11AX and all of that. And we'll go into more detail about OFDM and OFDMA later in the coming sessions. So how does OFDM work? So what OFDM does is it says, okay, this is the amount of spectrum available. Let's assume that you have 20 megahertz channel. So I have 20 megahertz of frequencies that are available for me to transmit. Let me break them down into smaller chunks or subcarriers. Now, traditional frequency division multiplexing works this way. This is user 1. The x-axis is frequency here. So user 1 is using these frequencies. User 2 is using this frequency. User 3 is using this frequency. And there are gaps, which means that there are guard bands. So there are, for example, I can use from 10 megahertz to 20 megahertz. That frequency is for user 1. And then I'll leave about 2 megahertz for guard bands as a gap. And then I'll use from 22 to 32 for the second user. And then I'll leave another 2 megahertz and so on. So that's how normal frequency division multiplexing works. What OFDM does is it says, let's shrink all of that into, let's pull all the users closer and let's overlap one on each other. And that saves this bandwidth. Now, how are you able to successfully transmit when users are overlapping on each other? The way you do that is by using the orthogonality or the orthogonal nature of the waveforms. So for example, what we're doing here is, this is the first waveform that is in red color that's being transmitted. Rather than completely separating the red and the blue waveforms, what we're saying is there is the next wave that is being transmitted right next to it, but in such a way that when the red wave is at its peak energy level at this point, the other two subcarriers or waves are at zero energy level. So you can see that the purple and the bluish color, these two waves have zero energy at this point. That means that these waveforms are not interfering with each other. Whenever this guy is at his highest peak point, the other two are at zero energy, right? And that is what is called as orthogonality. That's how we are achieving orthogonality between the waveforms. So that is the reason why it's called orthogonal frequency division multiplexing. So we are dividing frequency and we are multiplexing information, and we are doing it in an orthogonal way. So that's why it's called orthogonal frequency division multiplexing, right? And this is the most common method technique that is used for most of the newer technologies protocols that are being used. So now, if you look at how OFDM works in the 11B and 11G and 11A standards, so you take the 20 megahertz channel that you have here, and you break it down into 52 subcarriers. Each subcarrier is about 300 kilohertz wide, like really not narrow. And then you carry information in parallel across all these subcarriers, and you basically pack the subcarriers so closely and make them orthogonal to each other. So now you are actually using the spectrum much more efficiently, and you can carry more information, right? And that is how we went from 1 Mbps, 2 Mbps, to 6 Mbps, 9 Mbps, 12 Mbps, and so on. Now, it's not just that. There are other things also we vary. We vary the coding rate, we vary the MIMO types, we vary a number of other things to get higher data rates. And all those things I'll cover in the next sections. But OFDM is one of those methods that actually helps you do this, get to different higher data rates and use the spectrum more efficiently. Right, so here are some references. So just to summarize, we talked about various things in this section. We talked about information signals. We talked about basics of modulation. We talked about the various spectrum frequency channels that are available in Wi-Fi. We talked about information signals, carrier signals. We talked about different multiple access techniques like frequency division multiplexing, frequency hopping, direct sequence spectrum, OFDM, and so on. And those are the things that we covered in this particular section. So next time, we will go a little bit deeper into the more complex modulation. We'll talk about QPSK, QAM, different types of QAM modulation rates. We're going to talk about MIMO, what is MIMO, what is multipath, and all these other interesting, fun concepts. We'll try to explain it in as simple terms as we can. So that's the session here. Thank you all for your time.